And thank you for being here. I'd like to introduce Dr. Faisal Alquaddoomi. He got his PhD in computer science from UCLA, and he's now part of the software engineering team here in the
Thanks for the introduction, Natalie. Hi, everybody. I'm glad to see that there's lunch, so you'll get something out of this. So today I'll be talking about Docker and Docker Compose. I'm calling this a crash course because it really is just an information dump. Just let it wash over you, get acquainted with it for the first time. And then, when you use Docker, come back to these slides and they'll help you remember some of the things that I talked about.
Are you going to send them out?
Yes, and there's a slide link at the end as well. Okay, so let's jump right in. So this is the overview. Why should you care about containers? And what is a container? What's an image? How do we find images? How do we run containers using Docker specifically? How do we create our own images and share them with other people? And then near the end of the talk, I'll talk about how do we orchestrate multiple containers together to build stacks, or what nerdy people call microservice architectures. And then at the end, there'll be some various topics that I'll touch on. I should mention that containerization is a huge topic, so I'm not going to be able to cover everything today, but I hope this is your entry point into this topic. So I'd like you to come away from this talk knowing what a container is and what an image is, how to launch and interact with containers using Docker, and basically the things in the overview, creating and sharing images, multi-container stacks, and also when you might reach for Docker and when you might avoid it. Please feel free to ask questions anytime during the talk. I realize there's technical terms that I'm blind to because I've seen them so often. And also I talk quickly, so feel free to ask me to slow down. Okay, some things that I'm not going to talk about are most security topics. I'm just going to kind of presume that you have control over the machine. But there are all sorts of ways to ameliorate the security concerns of Docker. I'm not going to talk about container orchestration. That's running containers across multiple machines. I'm also not going to talk about alternatives to Docker, how it integrates into the wider topic of open standards surrounding containers. But these things do exist. There are other build tools and container runtimes with more permissive licenses than Docker. And there are just entirely different container runtimes like Singularity. So yeah, feel free to ask about any of these topics at the end if we have time. But there's a lot of material to get through, so we may not. You can always, of course, contact me in any of the various ways that I have you contacted. Okay, so I love containers. I'm mostly a full stack web developer, and containers have made my life so much easier. I work in a lot of different environments. So I develop locally, I have to deploy things to staging servers, production servers, and having Docker as a tool to run the same stack reliably in multiple places is invaluable. So I typically create apps container first. I'll first make the container empty, and then I'll develop the app inside the container. And one of the benefits of this approach is that you categorize and document your dependencies as you develop your app. So at the end, you have a full image that anybody can run instead of having to collect it all and try to figure out how to reconstruct an environment elsewhere. And frankly, it's just convenient to be able to grab an image from here, an image from there, put them together, and have an application. So there's tons of public images available on Docker Hub, other places, and they're just ready to be used, and they have a pretty consistent interface because they're all part of this Docker or container ecosystem. So why should you care about containers? The main reason that people talk about is the works on my machine syndrome. So somebody writes some software, they send it to you, you have some inexplicable bug, and of course it's due to the environment. You have a different version of software installed, you have different configuration, all sorts of things. As you develop software, your environment will inevitably creep into the software that you're developing unless you're very careful to isolate it. So similarly, using containers helps to keep your machine clean of this kind of environment creep. So say I get whiz-bang tool A, and it requires dependencies 1, 2, and 3. Now I have dependencies 1, 2, and 3 floating around on my machine even after I'm done trying out that tool, right? So with containers, you can start them up, you can clean them out very easily. Because they're packaged as images, it's really easy to share them and to reuse them. So you can push them to, I'll talk about this later, public registries, other people can pull them, and because they all have this unified interface, it's easy to interact with them. On that note, it's easy to archive and reproduce research using images. So say that you've written a pipeline and you want that pipeline to be runnable 5 years from now, 10 years from now with the exact same software, you can create an image instead of hoping that the package repositories are still going to have those packages available then. And then finally, and for me, this is the most compelling aspect of it, you can run applications in stacks in isolation from each other. So I can start up 3 copies of the stack that I'm working on with different configuration and test them, or you can have 2 users on the same machine working on the same code. We have living examples of this with Mobile for a project that I've worked on for the JRavi lab. We have a giant server, and we can all work on the app in parallel because of this isolation. Okay, so I'm going to talk a little bit about theory before we get into some practice. I'm going to define some terms. This probably is a place you're going to want to ask questions if you have them. So first of all, what is a container? A container is a process, like any other process that you launch on your machine, Word or command line tools or whatever, but it's isolated from the host in several important ways. One, it's isolated from the file system. So a container has its own internal file system. By default, it can't access the host's file system, so it can't do things like overwrite your system configuration or read your emails or whatever. It's also isolated from the network, so it doesn't expose any ports, right? So it can't collide with other services, and you control. I'll talk about breaking isolation in the next slide, but you control how that mapping occurs from the host's resources to the container's resources. And also you can constrain things like CPU and memory. Now this is available on your operating system, typically using C groups, and that's how it's implemented in Docker. But you can say, okay, I don't want this container to take up 1 GB of RAM and only use these 2 CPUs, for instance. Important note, containers are not VMs. So I don't know if you've heard of virtual machines before, but the idea is that you run an entire operating system, typically under emulation, on a host, right? So this provides some strong isolation between the host and the virtual machine, but at a heavy cost. Literally, they're running an entire operating system, so there's tons of RAM that the operating system requires. You have this really strong isolation between resources in the host and the container, and there's all sorts of ad hoc mechanisms for like sharing into the VM, but it's never quite as good as a process would be that's just running on your operating system, like any other process. Okay, so as I mentioned, containers are isolated from the host file system, so they need a file system, right? Every process needs a place to find its executable code and other supporting files. So what produces that file system for the container is an image. Okay, so what's an image? Images, I had a person ask me a question a long time ago when I presented Docker about like, are images pictures or not? Because it's very suggestive, right? In a way that they are. They are a record of state, right? In this case, it's the state of the file system that's necessary to run your application. So you can think of an image as being kind of parallel to a program you download from the internet. The program sitting on your disk is an image, right? And when you launch that program, now you have a process that's running in your operating system, right? And if you were to click that program multiple times, you'd have multiple processes, all based on that same image. So similarly, launching a program to create a process, you launch an image to create a container. And these images are composed of layers. So images, I don't know what the current standard is, but they either use layered FS or squash FS. It's a special kind of file system where you have these basically like blocks of files that are ordered, and then each subsequent layer overrides the previous one. So you could have like an initial layer that defines like the entire operating system's files, and then layers that like define configuration that then gets merged into those previous layers. I'll talk about more of this later. Also, an important point, not all of these layers need to be located in this image. So images can reference layers from other images. So typically when you create an image, you'll base it off of an existing image and then like add additional layers, and then the image only needs to have those additional layers in it. This is great if you have like 100 images that are all based in Ubuntu. You don't need 100 copies of Ubuntu. You just need 1 copy of Ubuntu, and then they only store the differences from that base image in those derived images. This also saves a lot on effort of creating images because you don't need to like define Ubuntu every time you create an image, right? You can just base your image off of Ubuntu. Okay, so brief aside, let's talk about processes if you're not familiar with them. So process is just some code that's executing on your machine that's running in a this is kind of out of scope, but it's running in its own little memory allocation. And processes can create other processes. So when your system boots, it starts a process called process 0, and then that starts process 1, which is like the init process. And then from there, all of the other processes are created as children of those processes, and they inherit the permissions of the users that launch those processes. And when I talk about users, yes, there are human users who use computers, but there are also system users. And a user is just a collection of permissions, basically. And yeah, so the initial process is run as root. It has full permission over everything. And then it creates login shells for individual users, constrained permissions. And this hierarchy typically narrows in permissions as it goes down, right? So child processes have some of the traits of their parents, but they can be further constrained. They typically don't expand their permissions. We call this a privilege escalation in computer science. It's typically not a good thing. So yeah, privileged processes typically need to be owned by a privileged parent, much like life. So yeah, Docker containers are children of a special privileged process called the Docker daemon, which typically runs as root. I'm not going to get into rootless Docker, but typically runs as root. This is some person's process tree that I found on the internet. Don't know what's going on here. Okay, so what happens when you launch a container? So when you take an image and you launch it to create a container, the layers in the image are squashed into a file system, right? All of this is read-only, and then one additional layer is put onto the end that's writable, and this is called the ephemeral file system. So as the container is running, it's writing anything that does, anything that's written to disk goes into this ephemeral file system. As I mentioned, the container starts as a process that's a child of the Docker daemon. So since the Docker daemon runs as root, containers by default run as root. Be careful about that because, if you all know, but running as root can be destructive. You can overwrite essential configuration. You can access any file on the system, all sorts of things. Also, a container has one entry point process. All of the other processes that a container starts are going to be children of that process, and that entry point process determines the life cycle of the container. So when that process dies, the container is destroyed, along with the ephemeral file system. So this might sound bad, but it's actually a good thing because containers basically clean up after themselves. So they can still, read and write files, but those files go away and you get to start from scratch the next time you launch the container. Or if you have two containers, they have their own independent file systems.
When you kill a container, is it guaranteed to kill all the child processes?
Yes.
Guaranteed.
Yeah. And that's something that your operating system provides. Okay. So there are ways to orphan processes, but Docker typically doesn't do that. As far as I know, all of the processes are run in the C group, and the C group guarantees that everything gets killed. So that's a good question, though. Yes, Jake.
Is it possible, say you have this image with a few layers, say 5, and you launch a container and it has this final writable layer.
Mm-hmm.
When that container is done, I'm done using it, is it possible to actually concatenate that and save that state?
Yes, absolutely. Okay. So there's a command called commit that takes a container and converts it into an image, which includes the ephemeral file system.
Yes, I'm seeing a use case where I have this program and I do some sort of writing to the file system, and I want to save it after. That's something I could do.
Mm-hmm. In fact, you could just launch Ubuntu and then make a bunch of changes and then commit that, and that's another way to create an image. That doesn't involve a Docker file. But we'll get into Docker files later. But yeah, great question. Okay, so moving on, I talked about isolation, how good isolation is, but obviously total isolation is not the answer, right? A web app that can't take clients is useless. A tool that can't read or write files from the host, similarly useless. So there are a couple ways that we can selectively break isolation. So we can break network isolation by port mapping. So we can say this port in the container is the same as this port on the host, and they don't have to be the same ports. So you could, for instance, launch the same service that thinks it's running on port 80 on ports 8001, 8002, 8003. You can have as many copies of this as you want, load balance between them, all sorts of neat things that containers make possible with this isolation breaking. You can also break file system isolation in two ways. So the first is a host bind. So you take a folder on your, when I say host, but I'm talking about your local machine. You take a folder on your local machine and you map it into the container, and then it's a bidirectional mapping. So any changes you make in the container go back to the host, any changes in the host go back to the container, and this process occurs immediately. They're actually unified in the file system. So something to mention about this is that when you bind things into the container, they shadow the contents of the layers before that. So like if you had a folder called like var my files, it was full of files in your image, and then you bind something onto it, say an empty folder, when you go into the container, that folder is going to look empty because it's shadowing the content in the image. I mention this because it's a point of confusion for people often. Like the files don't get merged together if you mount a folder or something, it just shadows it. The other kind of file system isolation that you can break is using named volumes. So as I mentioned, this ephemeral file system gets deleted when your container ends. But say that you want something to persist, but you don't want to try to find a place on your computer to store that data. So Docker has this mechanism called a named volume where it will create a special folder that Docker manages that you can then map into your container. And this volume will persist between container runtimes. Like so your container will end, you can start again, the data will still be there. You can share this named volume between containers, and then they can kind of collaborate in a private space. They can share files there. So I'll talk more about how you break isolation in practice when I talk about running containers. Okay, another side, I've talked about images a lot, but how are images defined? So images have a name and they have a tag, where the tag identifies variations in the image. And the tag is something you can freely assign when you create images. But the idea is that like the name is like a type of thing, say Python, for instance, and then the tag could be a version. You could have like versions of Python images that are based on different operating systems. So like there's a popular operating system for Docker images called Alpine. It's super small. So people will often create like Alpine versions of Python or Ubuntu versions of Python. Ubuntu is like all the batteries included, Alpine's super small. And then they'll be like differentiated with a tag. So you'll see like 3.10-Alpine, for instance, or just 3.10, which is probably the Debian version of Python. Images are usually stored in registries. Registry is a special kind of service that just stores a collection of images and then has semantics for being able to pull those images and push images into the registry from the command line or wherever. So they're organized by name and tag and they're accessible via the web. It's actually like an HTTP service. You could like connect to it directly and just look at what it's sending back and forth. The Docker daemon pulls from registries in order to create, to download images and then to create containers. And you always have a local registry that whenever you pull, it actually ends up in the local registry. The local registry is kind of like a cache of images. And when you build an image, it's also stored in that local registry. As a pre-step, when you pull, it's stored in the local registry, and then the local registry is actually used to construct the container. Which I say here. Okay, so in addition to the local registry, registries can be remote because Docker, the organization made this product. They, of course, made their service Docker Hub the default. You can browse images that are stored in Docker Hub at this address, hub.docker.com. There's all sorts of images there. There's official images that are just, they're defined by the organization underscore. And then there are organization-specific images. So like you can go to Docker Hub, create an organization, and then you can put your own images there. And that's like an easy way to share them with people. There are a bunch of other registries as well, though, since the registry is itself a container that you can just run wherever you want. So Google maintains an artifact registry. Amazon has one, it's the Elastic Container Registry. And then there's the GitHub Container Registry as well, and there's a bunch of others. And as I mentioned, you can literally just run a registry yourself by just Docker run registry. And as I mentioned, full specification of the image then is first the registry, followed by a slash, followed by an organization or some other identifier that like is specifically overridden by these other registries, and then followed by the name of the image and a tag. So if the registry isn't provided, it's docker.io. That's the domain name for the Docker registry. You can put other things here. ghcr.io is the GitHub Container Registry. An organization, I think, in GitHub is like GitHub Works. I don't know what it is in Artifact Registry, probably project IDs. But on Docker Hub, it's an underscore for public images, and then if you have an org, it becomes that. And if you tag an image with this full tag, like if you name it that with registry organization name and tag, then when you push the image, it uses the registry to find the registry portion of its name, to find the registry to push it to. And then all of this other stuff just organizes it in that registry. So yeah, I'll talk about pulling and pushing images later on. Okay, so that's a lot of theory. So we'll get into some practice. I apologize if your eyes are glazing over. So now I think we're in a good position to understand this diagram. So you'll mostly be interacting with Docker through the Docker command. That's what's on the left-hand side here, also called the Docker client. Yeah, it's just a regular command line tool called Docker, and it has a bunch of subcommands. And these subcommands interact with the Docker daemon, that privileged process that I referred to earlier, to launch containers, pull images, etc. And the Docker daemon will fetch things from registries. So please ignore the extensions and plugins. These are features I don't really use in Docker. Right, so as I mentioned, you'll interact with Docker via this Docker CLI command. You'll typically be using like subcommands of it. So they'll be identified by like an entity name. So like if it's something to do with images, it'll be Docker image and then the command to do the images. A lot of these commands have aliases. So like Docker image pull, you just run as Docker pull, it'll presume that it's Docker image pull. Also, I regret not having a slide about this, but when you download Docker desktop for like your local machine, it comes with a GUI, a graphical user interface that like allows you to browse containers, search for images, etc. Yeah, that's just bundled along with it. I believe it's called the Docker dashboard. But as you become more used to Docker, you'll find that it's just, in my opinion, easier to deal with it from the command line than it is to get into the GUI. Not everything is available in the GUI, and sometimes the organization is a little strange. There are tons and tons of Docker subcommands. I'll only be covering what I consider to be the most important ones today. And yeah, you can always look at the reference here. It's an excellent reference. Everything is completely documented, so please make use of it. Okay, so let's talk about how to actually run containers. So the main command for that is Docker run. You specify an image, and then you specify a command optionally that you want to run inside of that container. So there's an optional flag IT, which is kind of nerdy but interactive sudo tty. It's actually two separate flags that are combined into one. That basically says like I want to attach to this container, and I want to type things in, and I want the process, the entry point process, to receive them and interactively put out output. If you don't run it with IT, you won't be able to type stuff back to the container. It will just run, and you'll see it's lost. You can also specify a -d flag here if you just want to run it and immediately send it to the background, so you're not attached to it, even to view the logs, which is useful if you're just running a service or something that you want to be backgrounded. So once you run containers, you're probably going to want to be able to find them. So that's when you use Docker PS. This is analogous to like the PS command on in Linux. It shows you a bunch of processes that are running. So this lists all your running containers. Importantly, it shows the ID of the container and its name, which you'll use for the rest of these commands, like Docker stop start and Docker rm for remove. So if you just want to stop a container, but you don't want to like delete the ephemeral file system, you can stop it, and then later on you can start it. So stopping it will like release it from using memory and CPU, but it won't release things like port mappings or volume finds or anything like that. You'd have to remove the container in order to release it from a port or from a volume. Any questions so far? Am I going too quick? Maybe it's too dense. Okay, well, as I said, this is a reference, so you might find yourself using this in the future. Okay, so as I promised, let's talk about breaking isolation. Primarily, you'll be breaking isolation when you run a container, right? So, and as I mentioned, there's two ways to break, or there's two important isolations we can break. File system isolation, we can do that via bind mount or a named volume, and the syntax for that you pass to the Docker run command is this -v or volume if you want to spell it out. And then the source is either a location on your host file system or a named volume. And it knows it's a named volume because it doesn't begin with a slash. Note that these are absolute paths that you pass as a source. And then the destination is the location in the container file system where you want that thing to show up. This is deceptively convenient. Often, like when you use applications, you have to like arrange everything into a specific file system for it to work. With Docker, you can freely map any folders or files you want into the file system that this container expects. And then, yeah, you don't have to do a lot of work of like trying to mimic that file system. I didn't document it here, but flags, there's really only one interesting one. It's RO, read only. So you could map you could host bind something and then not allow the container to change it. So only the host could be able to change it, so be able to observe changes in the host, but it wouldn't be able to change things in there. So that's convenient if you have like, I don't know, SSH keys that you're mapping in there that you don't want the container to mess with or things like that. Or really just any static data that you want to be guaranteed isn't changed. Yeah, as I mentioned, the this mount into the container will shadow the content that's there with whatever it is you're mapping in, so be aware of that. Yeah, as I mentioned before, you can also break network isolation, and this is done with the -p or --port flag. And by the way, you can typically read these commands outside in. So like the first thing is what's going on the outside on the host, and then the second thing is what's going on in the container. So for instance here, this is the host, this is the container, this is the host, this is the container. Whenever you see a colon like this in mapping, it's typically host first. Actually, I can't think of an exception, so let's just say it's always host first. Yeah, and if you're not aware of the fact, ports are exclusive on operating systems. So two processes that try to get the same port, one will get it and the other one will get an error. But because we can freely control these port mappings, as I mentioned, we can just assign them to increasing ports, and we don't have to get in and configure the services to run on different ports, which, depending on the service, can be complicated. Okay, just for the sake of completeness, I mentioned how to manage named volumes. So remember earlier we were talking about how this source doesn't have to be a path on the host, it can also just be a named volume. Docker will create it the first time it sees it, and then every time after that it will just use it. But because these are entities that are outside of the lifecycle of the container, they can accumulate. So you want to be able to monitor them and delete them if you need to. So you can use volume ls to show them. You can use rm to delete them. Note that no container can be used in that volume in order to delete it. So first you have to stop and remove all of those containers, and then you can delete the volume. And finally, you can inspect volumes using Docker volume inspect. And the one useful thing that this gives you is it shows you the location on the file system where this named volume is actually stored. Docker doesn't like to expose this information typically because it's really not important. There's not a lot you can do with a named volume, but if you really need to get in there and debug it, you can get that information. Yes, Milton.
Faisal, what's the practical difference between a bind mount and a volume, name volume? It looks like it is just a shorter way the volume to do it, but I don't know if there are other differences.
So it's essentially a host bind. I mean, it is living on your machine somewhere, but it's managed by Docker. So for instance, if later on I'll talk about Docker Compose, you can use name volumes of Docker Compose, and then it has a shorthand for when you tear down your Compose stack, it deletes all the volumes that are associated with it. So it can help to clean up after itself. And it also helps with permissions. So one thing about host binds that I probably should have mentioned, and I might mention later, is that when you bind to a folder on the host, the user IDs and group IDs and permissions associated with them are retained. So you need to make sure in your Docker container that you have the same user IDs and group IDs. Usually this isn't a problem because containers run as root, so they kind of just ignore all of those permissions. But if a container isn't running as root, then a volume, you know that you're guaranteed to be able to read and write to it. Docker makes sure that you have the permissions to modify it.
Yes, perfect.
Sweet. Okay. Yeah, so volumes are basically just convenient host binds that are managed by Docker. Okay, so let's get into a little bit of you have containers that are running and you need to get in there and do stuff with them, you need to debug them if it's a background container. So Docker exec will allow you to run additional processes inside of a running container. These processes are usually shells. So you'll Docker exec in bash, for instance, and then you can get in there and look at the container's ephemeral file system. You can interrogate processes that are running inside of the container, things like that. It's handy for that. You'll want to probably specify the IT flag when you do that because you'll be interactively using that shell. Docker logs, it's really useful as well. So as I mentioned, every container has an entry point process, and that entry point process is emitting output on standard out and standard error. And using Docker logs, you can see that output. And if you pass this -f flag, it will just attach to that process and continually output whatever that process is outputting. And you can press Control-C to detach from that log. But critically, unlike attaching to a container and viewing the logs, pressing Control-C won't send a signal to that container to kill it. it'll just disconnect you from the logs. So that container will continue to run in the background. You can use Docker inspect to get a lot of information about the container in JSON format. This can be useful for finding out like if there are host binds in a container that you forgot about. You can see those mappings, you can see port mappings, you can see the provenance of the image that it's running, various tags that are associated with the container and the image. These are more complicated topics than I'm trying to get into today, but it's a useful command. It's good to have in your back pocket. And then finally, Docker stats shows like a live dashboard in the command line of the containers you have and the resources that they're using. So memory, CPU, number of processes that they're running, network IO, all sorts of things like that. It's handy to like profile containers using Docker stats, although there are better tools for it. Docker desktop specifically, yes.
Is there a way to preview the file system of an image before you launch a container? Right now?
Good question. So generally no, but you can override the entry point using -- entry point when you use Docker run, and then you can just specify it to be a shell, and then you can get around and look around in there.
Okay.
Yeah.
Because I'm thinking about the use case. A lot of these bioinformatics tools, they have like maybe you start in /data or something, but you don't know where these other tools are in case you want to modify the image yourself or do something non-standard, I guess.
Yeah.
So it could be good to preview it, but yeah, I'd use the entry point approach said before.
As far as I know, that's pretty much all you've got. Hey, actually, I think Docker Desktop, the dashboard, does have a feature for like viewing the file system in an image. Yeah, personally, I found it easier to just get in there and look around. But yeah, maybe I'll follow up after this and see if that's possible. Yeah, good question though. Okay, so as I mentioned, images are stored in registries. Use the Docker pull image command to pull a remote image into your local registry. And note that these remote images will be pulled, each layer will be pulled in parallel. So this is already a good optimization. And any layers that you already have won't be retooled. So like if you've downloaded Ubuntu 22.04 before, and you have about images that you're downloading that are based on that, you won't have to redundantly download those layers. So you can also exchange images as files using save and load, but you don't get these optimizations. So you don't get this like parallelized layer downloading. You don't get it. It will still just get everything, right? Because you're just getting a file with all the layers in it, right? You're not going to be able to. It's not going to realize that these layers are aliased in other places. So you'll have to get them all. But I will say that this is convenient for like archiving images long term. So if you have the image on your file system, you know that you can always reconstruct it, right? You don't have to rely on the registry. And I should mention that the Docker run image will, if it doesn't find this image locally, it will implicitly pull it. So you don't typically use Docker pull unless you're doing something special. So we've talked about getting images. Now let's talk about creating images. And you create images via Docker files. So a Docker file is a plain text file. It's a series of instructions that describe how to build an image. And when you build an image, there's also this concept of a context. So this is a folder that you can use to copy. It's a folder on your host that from which you can copy files into the image. And anything that's like outside of the context and like a parent folder is inaccessible. So you should be careful to define what your context is. Also, the context gets copied into the Docker daemon. Should have mentioned it here, but you can define a .docker ignore file that can blacklist things from being copied into the context. But say that like you define your context file, or your context is a folder with like a ton of data in it, like say, I don't know, blast databases or something. You'll end up with like a 30 gigabyte context, and it'll take forever to even start building the image. So be careful about what you define your context to be. Use a .docker ignore to selectively ignore things that you know are not going to be in the image. And generally, you should try to keep your images small because it's difficult to transmit large images. It's difficult to deal with them, right? If you have additional data, you should consider using host binds to like bring that into the container, and then just document that when you distribute your Docker image that it expects these host binds. Does that make sense? I know it's on the slide. I apologize. Yeah, so there's a couple things here. The T is for tag, so that just defines what the image's name and tags is. This follows the same image like format that I discussed earlier. Context is the folder that all of the files that end up in the image are going to come from. And then by default, Docker assumes that your Docker file is named Docker file, but you can override that using -f and then whatever name you want for your Docker file. Okay, so actually, I think I'm going to skip ahead and just show you a Docker file. So here's a Docker file. This is an example Python application. The first line is what image it's based on. In this case, we're basing on Python 3.10. We define a working directory. So for those of you who are familiar with Linux, like in a shell session, you typically have like a location that's assumed to be where you're working. So if you like create a file, it's created in a working directory. You know, if you don't specify an absolute path, it's assumed to be relative to the working directory. And your container similarly can start with a working directory. In this case, we're calling it app. So for those of you who are familiar with Python, often a file called requirements.txt is distributed with Python packages and projects, and this enumerates all the dependencies of that application. So here we're copying that from, assumedly it's in the context, it's in the root of the context, and we're copying it to a location temp requirements.txt, and then we're using a Python tool called pip. This is a Python package management tool to install those requirements into the container. Note that I'm not using sudo or anything because the container is being built as root. You don't need sudo. You have full access to the container's file system. So what this is going to do is basically populate this image with these dependencies. Later on, we copy in the application source. And then finally, we set up the entry point for this to be Python. And then assumedly, there's a file called app.py that was copied in here when we copied everything from the context into the working directory. Why did I split this up into two things? I will now go back. And so I think we kind of got a feel for what was going on by just looking at that Docker file. So the first line is from the image it's based on. Talked about working directories, talked about copying files. Run, this is just executing arbitrary shell commands. So like if I was on a machine, I would run pip install, right? Similarly, I use run in the Docker file to run that command and alter the file system in such a way that, you know, like that thing is done, right? So for instance, if you needed the curl tool, you could run apt-get install. Curl, apt-get is the Ubuntu and Debian package manager. And curl is a tool for like doing web requests. So yeah, it's as easy as that. So you can specify all of your binaries, you know, just as these like run package manager install commands. Sometimes you'll define an entry point. Typically you don't, because the image that you're basing it off of will already have an entry point defined, which is typically the shell. So finally, the command is what gets fed to that entry point command to actually like launch your container. And the command is easy to override. The entry point is usually not. Some containers will define the entry point to be like some tool that the image is supposed to encapsulate. So like the blast image, for instance, the entry point will be defined as blast, and then the command will be arguments to blast. But most container or images you'll find will define the entry point as the shell, and then the command will be a shell command. So like Python, for instance, from my example, this is just being run as a shell command in bash or whatever shell it is that's defined in that image. So most of these instructions, copy and run, will create a new layer, as I mentioned before, and then your image is a concatenation of all these layers. So how do you choose base image? You can go with the generic operating system image. Debian or Ubuntu is good. If you need something that's just like got everything that you would expect in a Linux installation. Alpine is good if you want a really small image. The Alpine is typically like 30 megabytes, it's super tiny. And the Alpine package manager is called APK. This is good if you just really want a bare bones image, but it does not include anything. And then Scratch is kind of fun for just research interests. Literally no layers. So you start from scratch, define an entire operating system from scratch if you want a really, really small one. Yeah, so in addition to these generic OS images, there's also language-specific images. So they typically include like a runtime for that language, and they're typically tagged with different versions of that language. So there's some for Python. I've linked to the Python Docker Hub page. Not only does this have a list of these images, it also has instructions on how to use them. So like they expect different environment variables, things like that. It's all there. For R, the Rocker, R in Docker project, has tons of useful images for R. It's got base R images, it's got tidyverse images, it's got RStudio images. Pretty much anything that people typically use is going to be an image, and it's going to save you a ton of time because a lot of our libraries need to be compiled from source. And yeah, so you can use Rocker R for this. This is lovely because now you can be running multiple versions of R, which is usually a difficult thing to do, you know, in parallel on your host. And you know that you're starting from scratch too, which is great because I don't know. At least my personal experience with R has been that like the environment does get involved often. So you can inherit from any image, by the way. So even images that are intended to be used as is, you can base your image off of that, and then you can override things about it by adding layers. So you can take the Nginx image, for instance. Nginx is a reverse HTTP proxy, and you can add custom configuration for it as layers, you know? Yes.
Can you only add layers or can you subtract from existing states?
You can only add layers, but those changes can be destructive. So like
Adding a negative, I guess.
yeah, exactly.
Okay.
Yeah, so like if you like RM, you know, add some folder, it will be deleted effectively, but it will be an additional layer.
Good.
Any other questions? Looking good? Okay. So let's talk about some, yes.
So when you're inheriting from multiple images, do you override the entry point also?
You don't have to, but you certainly can.
Okay.
So if it's an OS image, you won't override the entry point because it's already set to the shell. And you'll just specify you will almost always specify the command at the end of your Docker file. But it's up to you if you want to override the entry point. If you're building like a standalone tool that you know you like always use that tool, and you want the command to be interpreted as arguments to that tool, then you would override the entry point. So I guess that answers the question. Okay, so there's a couple principles with writing effective Docker files. One of them is layer caching. So every layer that's constructed is cached by the Docker build system. So the first time you build your image, unfortunately, there's no cache, so the H time you build from scratch, right? But the next time you build your image, if nothing has changed to that layer, just pulls it out of the cache super fast. But if something is changed in that layer, say like we go back to this example where we have requirements.txt, and I change and I add a requirement, not only is this layer invalidated, but everything below it is invalidated as well, because now we no longer know that that change didn't introduce something that would make these invalid, right? So all of the layers below this have to be rebuilt. That's also why I separated requirements.txt from copying the app source. We'll talk about that here. So yeah, editing the Docker file to add any instruction that validates layers that follow it. Copies invalidated if the files change. And all the other instructions are never invalidated, as long as you don't change the instruction. There are ways to get around this. If you really need a layer to be invalidated, like say that you're pulling from, like you have a run command that pulls from a web source that you know is changing, but like you can't change the run command, there's cache busting parameters that will just say, never cache this layer, but then everything below won't be cached as well. So be careful with that. But they're available if you really need them. I would personally recommend, if you embed URLs and run commands, to like use attributes in those URLs that will change. So like if you're pulling from Git repo, you can embed the commit hash in the reference to pull from that Git repo, and then you can update the commit hash, change it, and then you have the nice property of if the commit hash doesn't change, you get to use the cache, as opposed to just cache busting it and having it pull every time. So in my opinion, it's critical to exploit the layer cache to speed up development, because you're going to be able to build these containers over and over and over again. So because of that, a few principles. You should order instructions from least likely to change to most likely to change. So expensive operations should also come before less expensive ones. And then finally, copying an application source, this kind of comes out of this, should always occur near the end, because that's the thing that's most likely to change, right? And it's also the cheapest thing to do, right? Just copying from the context into the image. So keep those principles in mind. Let's go back to the Docker file and talk about now why I organized it like this. Now, I could have taken this and just moved it up here, right? Copy in the app source. But then every time I change anything in my application, I'm invalidating this dependency installation, and I have to wait for it to install these dependencies over again. So that's why it's organized like this. Even though it's redundant to copy requirements.txt twice into the image, that's why, because of layer caching. see. Okay, so another point about writing effective Docker files is that Docker is in some sense a process manager. So it's helping you run individual processes, monitor them, kill them, inspect them, etc. But you could, let's just say you naively were creating a web app, the database, you have two processes, right? The thing that's serving your website and the database, right? You could have an entry point that just runs the database, backgrounds it, and then runs the web server, or vice versa. But now you have two processes running in the same container, right? They're both children of the entry point process. Now it's a little bit unclear what the entry point process is. But yeah, it's bad for a number of reasons. First of all, it's just more difficult to write this Docker file, right? You need to think about this process that's being backgrounded. If you have a whole bunch of these services that you're relying on, you have to background them all. Now you have to construct some kind of process manager of your own to manage these processes, or just trust that it's fine for them to live as long as the entry point process does. There's other issues there as well, like they're not going to get cleanly shut down if the entry point process dies unexpectedly or container's killed. It's more difficult to reason about the total state of the system. That kind of goes into having to develop your own process management scheme. And yeah, it circumvents Docker as a process manager. So I'll talk about the alternatives to running multiple processes, but generally avoid it when you can. Sometimes it's okay, but typically there are better solutions. So just for completeness' sake, here's a laundry list of commands for managing images. So we talked about build, and then in addition to that, you can list images, remove them, pull them, tag them. This becomes important when you're going to be pushing local image that you made to a remote registry. So you can take the name that you gave it in the tag and then specify that full name for the image, the registry, the organization, the name, the tag. And then when you push it, Docker will read that registry and will push it to the appropriate registry, whether that's Google or Azure's image registry or Docker Hub, etc. As I mentioned, you can save Docker files. You can save an image to a file using the save command, and you can load an image from a file and name it some image. This is useful if you really don't trust registries. You just want to keep a local copy of your image, or you need to run this image in some kind of protected air-gapped environment, say, that doesn't have access to the internet. You need to bring your image on like a flash drive or something and then run it in this like isolated Docker environment. Finally, there's Docker image history, which shows you the commands that were associated with each layer in that image. This can be useful, but you lose a lot of context. Literally, you lose the context, right? You can't see the context of this. You only see the commands that were used to construct the image, but it can be helpful. Especially if it's an image that just consists of run commands and doesn't use the context. A lot of the operating system images are like that. It can be useful for vetting images or just doing, forensics. Okay, brief aside on architectures. So computers are designed around architectures, right? Linux and Windows PCs, their processors have a defined set of instructions for their machine code, right? And typically Linux and Windows PCs are x86 or AMD. A lot of new Macs, this kind of just came about recently, actually, this whole architecture confusion, because Apple decided to like cut left real hard and target the ARM architecture for a number of reasons. But now there's two common architectures in the world, ARM and x86. So because Docker images contain binaries that target, they're written in machine code for a specific architecture, you can't just run an image from an x86 architecture on an ARM architecture. And by default, when you pull an image using Docker pull, it will implicitly pass your platform or architecture to the registry, and the registry will try to find an image that's of that appropriate architecture, and if it can't, it will just fail. To get around this a little bit, Docker recently started bundling an emulator called QEMU with Docker Desktop. It's slow, but it's not too slow. It's actually feasible to use it for a lot of things. And if you know that your target, like where this application is actually going to be running, is in that architecture, you can run it under emulation locally to develop it, and it's fine. So in order to use that mechanism, you use the platform flag. So you would pass platform like AMD 64 to Docker build on Mac, and then that would build like a Linux or Windows compatible image. You can pass it to Docker pull to select a particular architecture image that you want. And you can also pass it to Docker run, and that will engage the emulation layer. And this is super convenient. Say you just want to run a Linux binary on a Mac or on a Windows machine. You can leverage QEMU to do that. Yeah, as I mentioned, there are some performance degradation issues, and also occasionally there are bugs in the emulation. Emulation isn't perfect, but it usually works. Also, it's not on the slide, but because of this like architecture bifurcation, Docker started to allow you to have multi architecture images. So like when you build an image, you can say, I want to build it for platforms A, B, and C. It will emulate the platforms that you're not actually running on and create an image that contains all of those architectures. And then if somebody needs an architecture that runs natively, they can grab that image, and then they don't have to deal with performance costs of running it under emulation, even though you have to deal with performance costs of building it under emulation. So any questions there? I realize it's kind of an esoteric point. Finally, I'm going to talk a little bit about some maintenance commands. So Docker manages a ton of resources: containers, images, volumes, etc., networks. And we can get into that in this talk. But you can get an overview of how much disk these are all using by using Docker system df. Then you can use Docker system prune to clean them up. So this deletes containers that aren't running, images that are dangling, etc. You can also specifically delete volumes that are not in use. So Docker doesn't do this for you automatically because it presumes that like maybe you're just in between running the container again, and you actually want that volume. So you can use Docker volume prune when you know that you're not going to use these things, and then we'll warn you and say, are you absolutely sure? And you press yes and delete your important data. You can also use Docker image prune to get rid of images that are not currently used. Similarly to volumes, Docker kind of presumes that like an image might be useful to have hanging around, because you might want to run a container from it later, right? But if you absolutely know that you're done, you want to clean up, you can run Docker image prune. Okay, so what time is it?
4 minutes.
Okay, great. Because the title of the talk is Docker and Docker Compose, I realized late last night that man, it's gonna be hard to get Docker Compose into here. But anyway, so applications can become complicated, and as I mentioned, combining all of the components of an application to a single container has a ton of drawbacks. So you can instead use a tool called Docker Compose to combine individual containers into a stack where these things can communicate with each other. And on the right here is like a standard 3-tier web application. It's got a front end, it's got a RESTful API, this can be written in Python, say. It's got some kind of background task executor, say Subary or something. It's got a Postgres database. It's got Nginx. You can see this is a lot of containers that all need to be orchestrated together in order to produce this stack. So, as I mentioned, Docker Compose, which comes with Docker Desktop when you download it, is a system for starting sets of containers that are tightly coupled to each other. So they're started together, they're stopped together. Containers can depend on each other, so you can say like, I need the database to be running in order to run the backend, and then Docker will make sure that the database is up and able to accept requests before the backend comes up and starts requesting things. It's also easy to declare shared resources like main volumes or shared environment variables that then the processes that are running these containers can use, like passwords for the database or something that need to be shared between the database and the backend, but would be difficult to orchestrate otherwise. I should mention Docker Compose is entirely optional. You can do everything you can do with Docker Compose with just straight up Docker run. It's just more work. These stacks that I described are defined as YAML files, and we'll look at one. So this is the YAML file for that architecture that I showed you earlier. So we have services. These are the containers. So we have a front-end container, we have a back-end container, we have a database, and we have this proxy, this thing that's serving, depending on who's requesting what, it's either directing requests to the backend or to the front end, or potentially the static files. So here, for instance, the front end and the proxy are sharing a volume called front end bundle. The front end, when it runs, will produce this bundle. So it'll like compile JavaScript down to like some kind of like static set of files. And then Nginx will serve that, and Nginx proxy here will also redirect API requests to the backend because it's actually need to run code on the backend container, right? And then the backend can query the database, do operations. Here we can see that the proxy is exposing some ports. This is port 80 is like the HTTP port. It's like what web servers listen on typically, and 443 is the HTTPS port. So this is like the first secure communication with web server. Yeah, you can see it's just mapping these to the host. Sorry that I'm going through this so quick. One last thing. The env file here This file is just a set of environment variables that you define, and both of these containers now get the same set of environment variables. Look, I have a question.
Yeah, do you have to worry about like file locks if you have two different containers reading from the same like directory and from the same file? Or are those like separate copies from each other?
They're not separate copies. You do have to worry about file locks. Well, I mean, worry or use them to your advantage because they're typically helping you. But yeah, they are actually joined to the same location in the file system. So yeah, and every operating system level file system protection applies. Okay. But it is useful to be able to share data between these two things, as you can see. Like, you can just set up Nginx to serve this thing. You could even map this to like Nginx's default directory for serving static files, and then you don't need to configure Nginx at all. But this container sees the same data as this path, and then this container can see it as a different one. It's a shame that it did not do that in this example. Okay, so Docker Compose brings the stack up. You can pass build to the up command to build any images. So previously here we referenced like build front end, build back end. These are contexts that presumably contain Docker files. And using this build flag, we'll just build the images before the whole thing runs. This is very convenient if you have like images you're developing locally and you just want Docker Compose to build them. By default, it will attach to the stack and tail blocks and kill the entire stack, and you press Control-C because you're attached. You can pass the D flag to Docker Compose to stop that. It will detach immediately. You can also, this is a feature I use quite a bit, but in addition, you can have multiple Docker Compose files. So I'll typically have a base Docker Compose file, and then I'll have a bunch of other Docker Compose files for different environments that override specific attributes. So like in production, I'll run an SSL terminating proxy, whereas locally I won't, or I'll expose ports locally, and then like in production, I won't expose those ports, So you can use this merging semantics for Docker Compose files to create some very elegant like deployment descriptions. Finally, yeah, tail logs, they're created on internal networks. They can talk to each other without being exposed to the outside. And if you want to totally clean up the stack, as Milton was asking before, you can run this Docker Compose down V, and this will delete all the volumes that are defined in the stack. Okay, let me just try to get through this real quick. When do you use Docker? When you have control over your local machine or the host. So like if you have a web server, some VM on Google Cloud or something, it's a good candidate for Docker. You just need to ship an image to it, install Docker, and run it, and you're good. If the thing you're developing is standalone, it's good. If it's not standalone, probably should put this in the one to avoid. You probably don't need a container because this thing is going to be in some larger ecosystem. Like if it's a Python package or an R package, it's going to be installed via that mechanism typically, and the containerization doesn't do much for you. Now, if you could imagine this package also being used as a command line tool, you might distribute a Docker image of it alongside the package version of it. But that's a special case. So when to avoid it? When you don't trust an image, it's fine, or know what it's going to do, then maybe it's not a good idea to run it. There are ways around this, but I'm not going to get into it. And on multi-user machines, so I mentioned the Docker daemon is a privileged process. So if it's not available in that environment, then you're kind of out of luck, right? So like HPC clusters don't typically give people root for obvious reasons, right? So Singularity is a common, Aptainer is the open source version of Singularity, which on Alpine, the CU Alpine is alias to Singularity, funnily enough. It has mechanisms for making Docker images into CIFS, which is like Singularity's image format. There are significant differences. So it's not like you can just take a Docker image and make it into a Singularity file. Like you need to think through all the differences between Singularity and Docker. They're surmountable, but it can be difficult. So where to from here? I realize this is a ton of information to digest. I apologize. Please use it as a reference when you get into Docker. The best way to get used to Docker is just to use it. It took me maybe like a month of using Docker on a daily basis in order to really get familiar with the commands and just remember them from memory. There's a ton of other topics that I didn't cover. Container orchestration, which is like if you've heard of Kubernetes or Docker Swarm. They're for running containers on like a cluster of computers and having them share resources. It's like a kind of a distributed operating system, you can think of it as, especially Kubernetes. And it also involves like scheduling containers on clusters based on machines in the cluster based on availability. If you use Slurm, it's doing a very similar thing. And unfortunately, I didn't talk about security or distributed builds or distribution or private registries or really a ton of other topics. But I hope it was somewhat worthwhile. If you ever want to talk, I'm more than happy to talk about containerization. And here's a link to the slides. And thank you for listening.
I just wanted to add a quick note that there is a recorded version. So if you're actually running through any of this, so you have something to refer. And then of course, Faisal is generally super helpful. So if the recording alone is not sufficient, you can reach out to Faisal. But thank you so much. This was a really good start.
Nice, thanks.
Okay. Any questions on Zoom, Zach? Or are we good?
Said this was fantastic. Thank you. Where can we access the video and PowerPoint afterwards?
Nice.
Michael, you can reach out to me. I'll have the video, and then I guess you want me to, I can just send it to the people who can.
Sure, that'd be good. So I'll send you the slides link.
Yeah.
Okay, great. Yeah, and this is also the link to the slides. Picture of it or something.
And I can also drop a note on Slack, on the real Slack, in case anybody couldn't make it, and if they want a video, they can request it on Slack.
I'm gonna stop here now.
All right, thank you so much.
Thanks, everyone.
You're gonna have some questions.
Absolutely.
About those easy ones.
Yeah.
I-
got
Okay. I won't check it out. Because the last chapter is what's there.
It's like a wrapper around the wrapper. It's something else wrote. Memory leaks.
You just have to do this kind
Just
why I know
just
that.
like will not terminate. And
I got you.
so basically.
That's why I said.
But
you
it's
know,
embarrassing.
not to say it will be bad.
So chop it up.
Yeah.
So it means
And it's
everybody.
like, okay, like,
I
it's
will-
still finished by X amount of time.
Yeah.
So I'm just doing doctor, I'm sorry, genetics, I'm just doing like this.
Yeah.
And stop, radon, it's basically.
I did all the ones on Thursday. If you want them, they're-
Yes.
All of these processes.
Okay, fantastic.
And they just.
And if you have a few
Or
empty
right
ones, then I
click.
can use it for.
Like,
You have a recommendation on like how I should like
Right now, we don't have
Common
any, but I
structure,
will-
Yes.
or like sidecar,
Alright.
all sorts of other stuff, like what would be the way that you would wanna set up the database service? And then have everybody just like write to it.
So I would definitely use a transactional database like Postgres or MySQL.
It's also kind of like DuckDB, but it's like the new hot.
DuckDB is not a great use.
No.
Well, so the problem, DuckDB is an in-memory database, so you don't get any of those transactional like guarantees.
Okay.
So you really need a database like server in order to like, you're gonna be getting like all these parallel requests, right? The database server will make sure that these are all consistent, right? Whereas DuckDB just runs an individual process and has no transactional.
Okay, so let's just think of it. PostgreSQL.
Yeah, so you'll just launch like one instance of it in your cluster, and then you'll have all of your parallel processes connect to that and write to a table or something.
Okay.
And then you can rely on it to correctly interleave those operations.
Okay, all right.
Kind of show me the code too, I can probably.
Okay, yeah, absolutely. It's still kind of getting glued together.
Okay,
Just
yeah.
like a mess. Yeah. Oh, and the other question I had was, so it's been probably about 4 or 5 months. I was trying to generate like different variations of like the Docker file, and I was just kind of just like typing it out to like different file, changing like little variables in the Docker file, but
Yeah.
I just kept on rebuilding the layers over and over and over again. So should I just do like that -F for like within like a state pipeline, or do you have like another suggestion for generating different Docker files?
Typically, I like to extract things that are different between like different builds as environment variables. So you, I don't know if you're familiar with the env instruction in a Docker file, but you can use that to like parameterize the running of the container, not the generation of the image. And if you really need to parameterize like the generation of the image, then you can use build arguments.
Okay, all right.
So, and then typically I just write a bunch of shell scripts to like generate a bunch of different images, different tags, but they all come from the same Docker file, and I just use those build args to differentiate them or variables.
Okay, all right.
And if you're on the chain, do that in practice, happy to.
Oh, absolutely, yeah. I'd love to get some feedback on that.
Right. Is that your, or is that mine? I'm pretty sure.
Not mine.
Oh, no, it must be yours, I didn't bring it.
No, I have no idea where this came from.
Oh, I think I guess it's
Did you not hand that to me?
No?
I'm fairly sure.
No, it's yours. Now it is. Yeah, whoever's most aggressive about it gets it.
No,
It's mine. Okay, it's yours.
I mean, it actually is fine.
Yeah.
I just thought maybe you had the same model.
No, I'm not even gonna buy out. I appreciate it. Thanks so much for,
What's your name?
I'm Casey.
Casey, and you're in,
I guess Kathy Lowe's opponents.
Oh,
Yeah.
yeah, I've seen you around in the 64.
Yeah.
Yeah, so I sit right next to Casey's office.
Oh, okay, cool. Yeah, I'm just like 10 feet away from you guys. Yeah. All right. Thanks so much. I appreciate you.
Do you have time for one?
Sure, yeah.
You can give a quick and dirty on running a Docker on HPC?
So typically it's like not possible. So you'll take your Docker image and convert it into a singularity image.
Okay.
If you have the relationship with the admins, you might be able to get them to let you run rootless Docker.
Nope.
Is
That's
it
not
out there?
No,
that's fine.
I unfortunately have to, because of, I work with indigenous tribal data, like I can only access and manipulate data from the Texas Biomed servers.
Hmm.
They're a fucking mess. They are running on old versions of CentOS 7, and I run into dependency incompatibility issues all the time. I'm trying to install software called EPACS, and I am starting to pull my hair out because I am running into C compiling errors, and I can't use Docker, and
You're probably just going to wrap the whole thing in singularity image. I think that'd be the easiest way to do it. So singularity and Docker aren't all that different. Like the analog of the Docker file is a singularity recipe file, and it doesn't do any layer cache or anything fancy like that, but you can run a bunch of commands as root inside of that image generation.
yes, I made a singularity file in my SnakeMake.
Oh yeah, it's not that. But so SnakeMake is like using that particular image.
Yeah.
But you might consider like wrapping the entire thing in another singularity image, and then you have full control over like, so you would like install SnakeMake into this image, and then your endpoint would be the image.
This is a completely separate thing. So like, I would probably just be taking the already existing Docker image for EPACS and converting it to a singularity image.
Okay.
Which I suppose I'll learn how to do.
Yeah, go for it. If you need help, as far as I can. I'm not super familiar with singularity, but I've used it before. So
I am new to all of it, so I'm learning as I go. A lot of things.
it's a wild world, and really it frees you from having to deal with admins, which I think is the best thing going on.
Yeah, I'm really tired of emailing Sandy. Mostly because they can't even get the group permissions for us, right? So I've had to email them daily for like months now. And then are you familiar with creating whatever files or using things to run things like SnakeMake on an HPC?
A little bit. I honestly don't use that
Like a
much.
configure file,
Like
like a configure.
I gotta collect the
It's-
designs.
I have to use SunGrid instance on this Texas Biomed server, and that also makes my life hard.
Yeah.
So I'm trying to figure out how to do more elegantly
One
use
chicken, one not chicken.
commands with SnakeMake for Q-subs and the equivalent of all these other things.
I actually heard last.
I don't know.
If that were gonna go to you, or it's gonna go to.
So my grandmother,
I mean, I'm
so funny, like,
Just if you had
there was.
had done that or had experience, because I know there's like
And I like was
at least
trying
for
to.
SnakeMake, they have a generic profile for selection brands that makes everything easier. They do not have one for this. Or, well, so the one that exists is out right now, so it actually doesn't has depreciated options that are necessary.
Oh my gosh.
I love,
I
So
love
I
controversies
have to
of the
either fix
rotisseries
that
and all
one or
that stuff.
I've never been.
You gotta go.
so I will say, our group probably should know that.
Thank you.
So it would be good for us.
I'm gonna go finish these things.
Do you need this card for everything?
No, I'm actually gonna use this.
Alright.
Where I've spent a lot of time learning snake making the last little bit, and I could come give an example with mine, because it does work,
Oh, nice.
and it needs finessing, but
Okay.
it can run a full-scale EWAS and should be completely transferable to. I run it on a cluster that doesn't have a scheduler. Just fine.
I see. Okay, cool. I mean, it's great to have a movie and example to work from. Let me photo with the group and see. It'll probably end up being me doing it, but I still need to talk to them about it because it's time. Yeah, I don't know. Do you have like a time scale for this, or is it kind of open?
I would send it.
Yeah, I'll see what they say. I'll get to it and see
Just
if
it would be
it's
helpful for you guys since you seemed to be interested in snake.
I have interest in it, so.
Or just you instead of the hospital.
Could be. You know, I actually can't follow my time. Is there
Thank
anything
you so
else?
much.
Yeah, of course. Sure.